Good morning, and thank you for taking the time to join me on this Ansys FEA Revision 16 update session. My name is Dave Goley, and I am a Senior Engineer here at Wild Analysis. This webinar is going to run for around 30 minutes, at the end of which we will have time for a question and answer session. I want to make you aware that all attendees are currently on mute, so if you do have any questions or comments, please feel free to post them directly onto the questions dialog box during the course of the webinar, and we will aim to address as many of these as we can at the end of the presentation. For the benefit of those who haven't spoken to us before or aren't familiar with Wild Analysis, we are an Ansys channel partner based in the UK. Our services include software sales, benchmarking, demos, training, after-sales support and consultancy for the Ansys user base. In addition, we also have a portfolio of other software products catered to specific industries or physics groups. I would encourage you to visit our website, wildanalysis.co.uk, and get in touch with us if you are interested in Ansys or any of the other software suites that we offer. Obviously, there is not enough time in this session to cover every single improvement that has been made since version 15. The topics that we will be covered in this webinar are based on those used most by our in-house engineers who use the software on a day-to-day basis, typically seen at the support desk, and those that have been requested by our client base. A full list of the new features and upgrades is available upon request. Shown here are the main sections of interest. We will look at contact, mesh settings, composites, rotor dynamics, fracture mechanics, fluid flow, and finally general enhancements. Starting then with the contact improvements. In this release, there have been significant improvements into how the contact stiffness updates during the solution. This has led to faster and more robust solutions. As can be seen in the table, version 16 shows a significant reduction in solution time compared to version 15. If we take the bracket case, for example, initially in version 15 this took 162 iterations. In version 16 this now only takes 121 iterations. And we've also found that in some cases, where version 15 was unable to obtain a solution, version 16 is able to converge and provide us with a result. General contact is a new feature which automatically defines all possible contact between individual bodies. In this example shown here, contact is automatically defined between every single plate with a hole in it. This method significantly minimizes the potential for human error and also reduces the time the user is required to spend setting up the analysis. Contact surface wear has been enhanced so that more accurate results can be obtained. The process is now significantly more automated and hence requires minimal input from the user in terms of the remeshing. And the solution will also be terminated once a critical stop value is reached. This means that the engineer can get on with other tasks whilst the solution is running in the background. Moving on now to contact trackers. I don't know if you use these much already, but they can be used to monitor the state of individual contact pairs during the simulation. They allow the user to monitor the contact in real time. This can significantly help with debugging troublesome models with nonlinear contact, and also save on solution time as errors in model setup can be detected before the solution has completed. In version 16, there is now the option to add these contact trackers after the solution has finished. This will enable you to see how the contact developed during the solution. Parallel contact detection. For large models, parallel contact detection has significantly sped up the time it takes for the automatic contacts generation tool to set up the contacts for your model. In this model, with 358 parts, 793 contacts were found. You can see here that in version 15, this automatic contact generation took 46 seconds, whereas in version 16, this now only takes 6 seconds. This speed up is achieved by taking advantage of the multiple core machines that most FEA users now possess. The last slide in our contact section shows a new formulation that is available to us for the bonded contact type. The beam option allows you to stitch bodies together using massless linear beam elements. The option requires 2 inputs: the material definition, which can be selected from the materials available in the engineering data, and the radius of the beam should also be selected. Moving now on to improvements in the meshing capabilities within Ansys Mechanical. The first improvement we have is the ability to plot the element quality onto the mesh. Previously, the only way to plot element quality on the parts themselves was by selecting a bar chart at the bottom of the screen, and even then it was only possible to see elements that have a specific quality. In version 16, we now have the ability to plot the element quality directly onto the mesh. This gives us a very good visual representation of where our good quality and also the bad quality elements are. As with the results post-processing that we have available to us in Mechanical, we can also highlight the minimum and maximum values and also probe individual elements. If we are not happy with the quality of our mesh, we have the option to manually move nodes to improve the quality of certain elements. The movement of each node is restricted to be along the face of the geometry that it is attached to. In the default mode, the node movement will be constrained by the boundaries of this face, or if instead we have selected a node that lies on an edge, then the node movement will be constrained by that edge. If we want to enable movement without restriction, then we need to press the F4 key to enable what we call Mode 2. This will allow the node to be moved anywhere so long as there is a face for that node to be projected on. This video shows how a couple of nodes can be moved. As we run through this video a couple of times, notice how the minimum and maximum element quality values in the legend on the left-hand side update during the node manipulation. You'll also see here that a table of node moves is created so that we can use this for reference to see what nodes we have in fact moved. Similar to auto-generated contact pairs, there is also the option to use mesh connections to join bodies together. The red line shown here on the left-hand side indicates that there is no connection between adjacent bodies. But after applying the mesh connections, it is possible to see that all parts are now connected. This is indicated by the purple lines. This is the preferred method instead of bringing in a multi-body part. By using the method highlighted here, we are able to take advantage of the parallel meshing features within Ansys Mechanical. What we mean by parallel meshing is that instead of each body being meshed sequentially, we can mesh many bodies at the same time so long as they have independent meshes. This parallel meshing feature is obviously not available with a multi-body part, as the mesh on each part is dependent upon the mesh with its mating part. Moving now on to remeshing. Until now, this has been a manually intensive process. First of all, you had to wait for the solution to fall over. Then you had to look at the mesh at the last few restart points and decide a new starting point. Once you had this new starting point, you then had to use the upjump command, create a new mesh, and then import your stress state onto this new mesh. Thankfully, this has now changed and the remeshing process is completely automated. The user simply needs to define a number of regions where they would like the remeshing to occur, and then the solution will take care of the rest of it for us. During the solution, the remeshing is highlighted in the convergence chart by the orange lines that we can see there. And there is also an additional column in the tabular data window to show when the mesh has been changed. This video here shows the remeshing process in action. As we run through the video again, if you keep an eye on the mesh towards the top right hand corner, you'll see how it is changing there to accommodate the deformation. So initially we start off with quite a coarse mesh, and as we run it through we end up with a much finer mesh there. I'll just run this through one more time. So looking next at Ansys Composite Pre-Post, which is more commonly referred to as ACP. There is a new function which allows us to make arbitrary cutouts into our structure. This can be useful if we would like to see the effect of a manufacturing defect, for example. We now also have the ability to import ACP plies into Mechanical. This will allow us to gain a better overview of the model content by using the familiar mechanical interface that we are used to. Within Mechanical, the plies are grouped as shown on the right hand side. Post-processing can be carried out in Mechanical, and we are able to view the fibre stresses within each individual ply. It is now also possible to convert legacy mechanical APDL composite models into Workbench ACP models. This will allow for model setup in a user-friendly interface. Unbalanced harmonic response of rotor dynamics is now available in Mechanical. In the image shown here on the left-hand side, it is possible to see how much the right bearing has stretched due to the unbalanced masses for each frequency step. The required inputs for the rotating force are shown here on the right-hand side. Small blade-to-blade variations due to manufacturing tolerances and wear produce large uncertainty in the force response levels of bladed discs. This is now modelled in version 16 using the mistuning model. Looking now at the crack object, this has been developed over a number of versions. The latest edition is the crack coordinate system. This new crack coordinate system allows you to align the crack with something other than a face. It is used in the mechanical APDL input file, graphics annotations, and fracture calculations associated with a given crack. The crack coordinate system can be orientated in a number of ways so that the crack is aligned as you desire. There is also a new user guide in the help files, which can be very useful in terms of helping you get to grips with what the crack object can offer us. And this can be found under Mechanical APDL Fracture Analysis Guide. The element named Fluid 116 has been available in Mechanical APDL for a few versions, but in version 16 this element is now available from the Workbench GUI. The thermal fluid flow analysis is equivalent to a reduced order modelling for a CFD analysis with a one-dimensional fluid flow. The analysis is able to solve for the 3D and 2D environments, and heat flow is generated by the conduction within the fluid and the fluid mass transport. The example shown here demonstrates the thermal fluid flow analysis in the model with two solid blocks which are heated by the fluid flowing between them. Two convection loads are participating in the analysis here, one between the fluid and the blocks and another between blocks and air. We'll move now on to looking at the general improvements that have been incorporated in version 16. These are not huge changes, but they will help in making the use of the software a little bit smoother. We will look at results post-processing, grouping of items in the tree, nonlinear buckling, modal analysis results, graphic enhancements, the beam tool, and the exciting sounding exploding geometry feature. A new results section in the preferences window allows us to set our default options for calculating the time history of results, and also whether or not results branches are automatically renamed. Results at multiple time points are easily created by selecting them in the tabular data section. Pressing the right mouse button, selecting Create Equivalent Stress Results, and then you can see there that the additional branches have been created quite easily in the tree for us. The user also has the option to select the Select All function. This will enable results to be created at every single time point. Object grouping allows the user to logically group loads and coordinate systems into folders to significantly reduce the size of the analysis tree. In the example shown here, over 100 bolt pretensions have been reduced into only a couple of branches in the tree. Non-linear buckling can now be considered in the model with or without additional loads. Unlike linear buckling, the load multiplier is calculated for incremental loads applied after the static solution considering nonlinearity. Ultimate buckling load of the nonlinear buckling is calculated as shown in the equation here. Eigenvalues can be computed either with or without the pre-stress load pattern considered. For previous modal analysis, it was necessary to scroll through the solve.out file that was created to find the relevant information on the mass participation factors, the effective mass, etc. Now, in version 16, when in the solution information branch, we now have the option of displaying this information in tabular format, as we can see here. So by default, all three sets of information will be shown, but as we have the option of filtering our results so that, for example, we could only show the effective mass if we wanted to. For any of you fortunate enough to have a Windows 8 version installed on your machine, you'll be pleased to hear that the image capture and record video options are now compatible with that release of Windows. We also have the new option of, when in the geometry branch, we can simply press Ctrl and C to copy the current image to the clipboard. This can then be pasted into another program such as Word or PowerPoint. If we choose the image to file option, we are now presented with some preferences. Here we can change the resolution of the image to get higher quality images if we so desire, and we're also able to change the font size on the legend to ensure that it is still readable on the images that we create. The tree can be filtered to show components that are only relevant to the visible bodies. In the example shown here, when we hide three of the bodies, you can see that the tree is also filtered to show only the branches which contain visible sections of the geometry. So you can see here we've lost solid 2, solid 3 and solid 5. The beam tool can be used to display the full solution of a beam. This includes the ability to plot the maximum and minimum stress values on the outer surface of the beams. The final general feature to tell you about is the explode geometry feature. For assemblies with a large number of parts, this can be a very useful way of displaying hidden parts and also seeing how one part interacts with another. It should be noted that the applied boundary conditions stay attached to each respective part, as you can see there on the contact regions shown in the bottom right-hand corner. A quick recap now of what we have covered. I've shown you the significant improvements in the contact settings, which will reduce your simulation times. In version 16, the user now has much more control over the meshing, to the extent that you are able to drill right the way down and manually manipulate individual nodes. We have seen some brand new features, such as automatic adaptive remeshing, and we have also seen that some of the newer features, such as the contact object, have been further developed. And finally, I showed you some general enhancements that will make your day-to-day use of the Ansys Mechanical version 16 software a little smoother. More information can be found in the full release notes contained within the help files. These can be found under the Ansys Structural Products branch, shown on the right-hand side. Just before I go, I'd like to make you aware of our upcoming webinars. We have the first one on Genesis topology for Ansys Mechanical, which is a new optimization tool within Ansys. That presentation is on the Wednesday before Easter at 2 p.m. UK time. The second one is focused on simulations for thermal and structural response of electronic components. That will be held on the last Wednesday in April, again at 2 p.m. UK time. We look forward to seeing you there. So thank you very much for listening. If you have any questions or comments, please feel free to type them into the question box, and we'll try to get through as many as we can in the couple of minutes that we have remaining available to us. I'll just have a look through a couple of them for you now. So the first one I've got here, what options do you have available in remeshing? Well, in terms of the scoping it to either bodies or faces, you're only able to scope it to a body. And then you must remember that the mesh must be a single order with tetrahedral elements. Once you've defined it on a body, you'll be then given a number of different options to specify how distorted you will allow the elements to be before the remeshing is instigated. Let's see what else we've got here. There's one come through here for what file type do you get out of image capture? Well, this is the same file types that we've been able to get in the past. So I think there's PNG, TIFF, JPEG, and maybe a couple of others. When you're asked to save it, you'll see the different options available to you there. There's a question here about the fatigue analysis. We'll come back to that offline. And all right, great. I think that's about it. Thank you once again for listening. Enjoy the rest of your Friday. Thanks. Bye bye.